Fundamental Manufacturing Processes video series, examining the tools and techniques of precision manufacturing. This program explores the basics of sheet metal shearing and bending. Two of the oldest and most basic operations in all of metalworking are shearing and bending. Shearing is the mechanical cutting of sheet metal by means of two opposing blades. It is used to cut large sheets of material into smaller, more manageable sections to be used in later operations. Shearing is also utilized to cut sheet metal stock around the complete perimeter of a shape to form a workpiece known as a blank. These workpieces are then used in operations such as forming, punching, and trimming to complete the part. Bending is the creation of three-dimensional shapes out of two-dimensional material. Bending is a fast, economical way to produce an endless variety of parts from sheet metal and plate, often without the need for secondary forming operations. In most shearing operations, the edges of two knives, a fixed lower blade, and a vertically moving upper blade meet progressively from one side of the workpiece to the other to shear the material like ordinary hand shears. The angle at which the upper and lower blades are aligned with each other is called the blade rake or shear angle. The distance between the upper and lower blades is known as the blade or knife clearance. Knife clearance is essential for proper shearing and is modified for different material thicknesses and strengths. As the blades come together and contact the workpiece, they partially penetrate the material. This builds up opposing forces in the stock. A crack or tear called the slip plane then develops on both sides of the material, separating the stock. The shear blades typically penetrate the stock no more than 1/3 of the stock thickness before the slip plane occurs. The exact amount of penetration varies with material hardness and knife clearance. On most shears, the upper knife is aligned at an angle to the lower blade of between 1/2 and 2.5 degrees. This angle helps concentrate the shearing force in the exact area of blade engagement between the two knives and starts the fracture on a straight line parallel to the surface of the knives. This inclination also causes the upper knife to move away from the lower knife during the shear. This ensures that the sheared workpiece, called the drop, will not become wedged between the two blades. Sheet metal shearing can be done within a shearing die and a stamping press, but is most often performed using a machine called a shear. A typical shear consists of a fixed lower blade mounted on the table or bed of the machine, and an upper blade secured onto a vertically movable crosshead. Other shear elements include the housing or end frame and the hold-down feet, which secure the sheet metal or plate stock to the table to prevent movement during the shearing operation. Shears are made in a wide variety of sizes and styles. They can be classified by the way the crosshead is powered, either manually, mechanically, hydraulically, or pneumatically. Or shears can be classified by the type of work they were designed to perform. The most common shear designs include gapless shears, gap shears, right-angle shears, CNC or computer numerical control shears, and iron workers. Gapless shears have side frames which support the power unit and are joined together by the bed and crosshead. Gap shears are used for squaring sheet stock and producing blanks. Because of the gap or throat opening in the sides of the frame, they can handle larger sheet lengths than a gapless shear. Right-angle shears employ two sets of dual blades set at a right angle for simultaneous cuts along two axes. CNC shears can be programmed to shear a variety of lengths from a single sheet. The sheet is automatically repositioned in the shear for each cut. Iron workers perform shearing of plate, structural shapes, and bar stock, as well as several other operations, including notching and punching. Shears must have some kind of gauge for measuring the part to be sheared. 4 primary methods of gauging include back gauging, front gauging, squaring arm gauging, and programmable gauging that can operate under computer numerical control. In back gauging, the operator pushes the material between the knives until it comes to rest against an adjustable stop or back gauge. The material is then sheared. For rapid, accurate cutting, electronic sensors in the back gauge automatically start the shearing process only when the stock is in the correct position. When the back gauge is used to shear wide drops of thin metal, the material often sags, causing an inaccurate measurement. To eliminate this problem, a sheet support system can be added to the back of a shear. Generally, a sheet support holds the workpiece in a horizontal plane until it is cut. The support then pivots down, permitting the workpiece to drop. In front gauging, the sheet is located with respect to the cutting edge by means of adjustable stops or gauges located in the table or front support arms. Squaring arm gauging, with the squaring arm mounted on the end of the shear, enables the operator to shear a 90-degree corner on the material. The squaring arm can be mounted on either end of the shear to distribute wear on the knives. Programmable gauging is highly accurate and is incorporated into most CNC shearing programs. Sharpness of the knife plays an important role in the edge quality of the part. A sharp shearing knife can cut tough materials because the sharp edge concentrates the shearing force in a very small area of the workpiece. Dull shearing knife edges deform the metal surface more than sharp edges, since the shearing stresses are spread out over a larger area. In addition to the sheared edge, there are 3 indicators of the quality of the sheared part. These indicators are the camber, bow, and twist that remain in the part after shearing. Camber is the deviation of the flat drop side edge from a straight line. Camber cannot be eliminated, but it can often be reduced by lowering the rake angle of the upper knife. Bowing is the tendency of the sheared part to arch in the center. This frequently occurs when narrow strips are being cut. Bowing is almost directly proportional to the rake angle of the upper knife. The bow, however, decreases as the width of the drop increases. It becomes negligible if the drop is wider than 4 inches. Twisting in the sheared material is generally proportional to the rake of the upper knife and to the width of the drop. Narrow strips twist more than wide ones, thick materials more than thin, and soft materials more than hard materials. Slitting is a common process in the coil processing industry and is a shearing process in which wide coiled stock is slit into multiple narrower coils. Slitting is accomplished using a slitting line, of which there are 3 basic types: the single loop, the double loop, and the pull-through. These slitting lines consist of an uncoiler or payoff reel, a slitter, a tension device, and a recoiler. The uncoiler reel holds the master coil on its inside diameter using a mandrel. The coil stock is then fed to the slitter by rotating the mandrel. The slitter holds parallel shafts containing rotary cutting knives. The material to be slit passes between these knives for a continuous shear. Since most master coils are crowned or bowed in the center, the processed center coils wind to a larger outer diameter than the end coils. The result is that the center coils pull tight as the end coils hang down loose. A tensioning device is generally employed between the slitter and recoiler to adjust for this length differential problem. The recoiler takes up the processed coils on a mandrel, where they are removed onto auxiliary handling equipment. Bending is a method of producing shapes by deforming the metal beyond its yield point, which is the material's capability to resist permanent deformation, but not past its ultimate tensile strength, which is the metal's ability to resist tearing. The forces applied during bending are in opposite directions, just as in shearing. The bending forces, however, rest between the material's yield point and its tensile strength. In shearing, the forces used are well above the material's tensile strength. As the part is bent, it undergoes a distortion so that the material outside the bend is forced to stretch under tension, and the material inside the bend is forced to compress. Between the tension and compression zones is an area where the material is neither forced to stretch nor to compress. This is called the neutral axis. The neutral axis is important since bending operations are calculated from its location. The extent to which a material deforms, whether in compression or tension, is proportional to the material's perpendicular distance from the neutral axis. Bending can be performed in dies in stamping presses and on various other types of equipment. The most common of these bending machines is the press brake, chiefly because of its versatility and ease of operation. Press brakes can be used for both prototype and short-run custom work, as well as for lengthy production runs. Press brakes can generally be divided into two categories, mechanical or hydraulic, depending on the type of ram drive that is used. The principal components of a press brake are the bed, which is the lower portion of the machine that supports the lower or female die, the ram, which holds the upper die or punch, and the back gauge, which can be either a bar or fingers at the back of the press brake that position the workpiece so that the bend is made at the desired point. In a typical press brake bending operation, a piece of metal is placed between the upper and lower dies and formed by means of the force and pressure exerted by lowering the ram. On some press brakes, the ram and upper dies remain stationary, while the bed holding the lower dies provides the force that bends the part. 3 contact points are involved in a bend: the tip of the punch and 2 points on the female die. The material is bent to the desired angle as the punch enters the die. The larger the die opening, the smaller the force required to form a given angle. The principal terms used to describe bending on press brakes are bend allowance, bend angle, bend radius, and spring back. Bend allowance is the pre-bent length of material that must be included in a blank to allow for any deformation that occurs due to the bending operation. The bend angle is usually the included angle of the bent workpiece. It can also refer to the supplementary angle formed by the 2 bent tangent lines. The bend radius is a tangent line where the flat, straight section of the part stops and the radius of the bend begins. Spring back is the tendency of the material to return to its original form. Spring back typically ranges from 2 to 4 degrees. Press brake bending is divided into 2 major categories: air bending and bottom bending. In air bending, the punch and the workpiece do not fully bottom on the female die. The workpiece, supported by high points on the die, wraps around the tip of the punch to form the bend. Air bending is highly versatile, since a large variety of bend angles can be made from a single set of dies. Another advantage of air bending is that it requires considerably less press brake force to produce a bend, 4 to 6 times less than in bottom bending. Spring back is a particular problem in air bending. Allowance for spring back is made by overbending and then permitting the workpiece to spring back to the desired angle. Bottom bending forms bends by letting the punch force the workpiece against the lower die. In general, bottom bending produces more consistently accurate parts than air bending. Bottom bending is usually used for applications requiring a high degree of accuracy and sharp corners. Because of the high tonnage requirement, bottom bending is generally limited to bending steel no thicker than 1/8 of an inch, or approximately 3 millimeters. Dies are the tooling that determine the shape produced on press brakes. The most common type of bending die is the 90-degree V-shaped die, but many other types are used to produce shapes, such as the acute angle die, the gooseneck die, the offset die, and the rotary bending die. Acute angle dies are usually used in air bending, where accuracy is not critical. Gooseneck dies essentially are V-bend dies, with clearance for return flanges. Since the neck of the die is usually out beyond center line, care must be taken to prevent overloading the die. Offset dies are typically used for long runs and require from 4 to 20 times more force for a single bend, depending on the nature of the offset. Rotary bending dies use a cylindrical rocker with an angular notch cut out along its length. As the punch descends, the rocker clamps the workpiece and bends it around a die anvil. The position of the workpiece and the stroke of the punch are critical variables in the bending process. Computer-controlled gauges have improved press brake accuracy and made possible the economical production of multiple bend, multiple stroke parts in a single setup. These programmable CNC-controlled back gauges are servo-driven and change their position automatically for multiple bends required on individual parts. CNC gauging is also used to control the depth to which the punch penetrates the lower die. Folding is another process used to bend parts. A folding machine consists of an integrated sheet support and gauging system that feeds raw material from the rear of the machine to a set of upper and lower clamping jaws. Once the workpiece is positioned and clamped, a folding beam sweeps upward, gently creating the desired bend angle, anywhere between 0 and 180 degrees. Folding machines are especially suitable for large or complex parts requiring multiple bends, such as metal doors and furniture, electrical enclosures, lighting equipment, elevators, and conveyors. Let's review the material contained in this videotape. Shearing is the mechanical cutting of sheet metal by means of two opposing blades. It is used to precisely cut large sheets of plate and sheet stock into smaller, more manageable sections, which are then used in later operations. Typical shears consist of a fixed lower blade mounted on the table or bed of the machine, and an upper blade secured onto a vertically movable crosshead. As the blades penetrate the material, a crack or tear, called the slit plane, develops on both sides of the material, separating the stock. On most shears, the upper knife is aligned at an angle of between 1/2 and 2.5 degrees to the lower blade. This angle helps concentrate the shearing forces and ensures that the sheared workpiece, called the drop, will not become wedged between the two blades. Common types of shearing equipment include gapless shears, gap shears, right angle shears, CNC shears, and iron workers. Slitting is a shearing process in which wide coil stock is slit into multiple narrower coils. Bending is the creation of three-dimensional shapes out of two-dimensional material. Bending is a method of producing shapes by deforming the metal beyond its yield point, but not past its ultimate tensile strength. The press brake is the most common kind of bending machine. There are two major categories of bending: air bending and bottom bending. 90-degree V-shaped dies are the most common type of bending die, but many other types are used to produce shapes, such as acute angle dies, gooseneck dies, offset dies, and rotary bending dies. The addition of computer-controlled gauges to press brakes has greatly extended their accuracy and made possible the economical production of multiple bend, multiple stroke parts in a single setup. The folding machine is also used in bending and is especially suitable for large or complex parts requiring multiple bends.